Okay, everybody, this is 1-7 piecewise graphing. Peace to all of you here. All right, so piecewise functions, what those are, you can see the definition on this first slide. Basically what it is a function where you have different rules or equations that you use for different intervals of the domain. So instead of having a situation where the entire graph is all the same equation, like it's just y equals x, something like that, the equation changes as you move from interval to interval. So a real life example of that could be, say you are looking at sales for, say, an iPhone, something like that. The amount of sales may change as time goes on. So maybe for the first 3 months, it's really rapid growth. So it's a really steep slope, but then it sort of flattens off. So you get a different sort of thing happening. So maybe it's steep growth for a while, and then it flattens out, levels out, and then maybe even starts to go down because of, there's a new technology, there's the iPhone, whatever. So that would be a situation where you'd have to use 3 different rules in the picture that I just drew to describe what's happening for the graph. And that's exactly what a piecewise function is. It's something where there's different rules for each part of the domain. All right, so there's 2 different kinds of graphs like this. We have what we call discontinuous ones and continuous. So if you take a look at the first graph, a discontinuous graph, if I try to trace it, and I'm going to trace this along so you can do that with me. If you trace the first little piece, it gets to an open circle here, it's a horizontal line. You have to lift your pen or pencil to start tracing the next piece. And then again, you have to lift your pen or pencil to trace the last piece. That would be what we call discontinuous. It's not something you can draw without lifting your pen or pencil. There's 3 different parts to this equation. There's this first horizontal, there's the slanted part, and then the third slanted part, which corresponds with the 3 rules down here. So there's 3 parts to the equation, but you can't draw it all without lifting your pen or pencil. So this would be a graph that we would say is discontinuous. So that is not connected. It's not a connected graph. The continuous ones, if you trace it, so you can trace along with me the second one, when I do the whole graph, I can do the entire thing without lifting my pen or pencil. So this continuous means connected. So it's a connected graph. So there's still 3 different pieces. There's the first slanted line, a horizontal piece, another slanted, which corresponds to the 3 different rules down at the bottom. But again, it's a graph that needs a different rule for each part of the domain. So those are the 2 pieces that we have. So there are 2 different types of piecewise graphs: continuous, discontinuous, connected, not connected. All right, so let's take a look at an example of something that you haven't done before. This equation that has brackets around it is called the greatest integer function. So when we look at the actual name of the function, it's called greatest integer. Some people, as kind of a nickname for it, they call it the step function, and you're going to see why once we make the picture. So for the step function, what you are doing is you're looking at different intervals of the domain that are going to give different graphs or different pieces for the output or the y. So the intervals I'll put over here. Those are your intervals for x, and then we're going to see what our value is for y. So I'm just going to pick some intervals I know work really well. So we're going to go from -2 to -1. We're going to go from -1, oops, I was putting the 0 already. Ooh, that's a big eraser. So -1 to 0, and then we're going to go from 0 to 1, 1 to 2, and then 2 to 3. You could continue going in both directions too. I just think this will give us plenty to be able to talk about and look at. So I'm going to start with this interval, or look at all these intervals, and notice that the first numbers are all with the equal to. So every one of these on the front end have equals to, where the other ones don't. That means the first end of the interval is included. When you graph it, it'll be closed dot. The other end is not going to be closed dot. It'll be open because there's no equal to. All right, so I'm going to start with this interval in the middle. It might be the easiest one to do. If you pick any number between 0 and 1, so I want you to think of a number between 0 and 1. What greatest integer says is that you have to round this number that you pick, this x value. So we're thinking of what is the greatest integer of, I'm just going to use a half. That's between 0 and 1. What those brackets mean is you have to think of the biggest integer, or the greatest integer, not bigger than your x value. So what's the biggest integer not bigger than a half? Well, it would have to be 0, because if you pick 1, which is the next integer, that's bigger than a half. So you're always going to be rounding down. It would be the same thing if you did, what's the greatest integer of a third? Well, the biggest integer not bigger than a third would be 0 because 1 would be too big again. You could do any number between 0 and 1, and all of those are going to round down to 0. That's the biggest integer, not bigger than those numbers. Now, when you get to 1, though, if you do the greatest integer of 1, well, what's the biggest integer not bigger than 1? Well, 1. So everything between now, starting at 1, going up to 2, so I'll pick another number. So we're in this second interval now, the next one down. Say 1.5. What's the biggest integer not bigger than 1.5? Well, 2 is too big, so it has to be 1. So all of these numbers between 1 and 2 would round to 1. Between 2 and 3, then, think of 2.5. Greatest integer not bigger than 2.5, it would round down to 2. So we have these numbers that are going to give us horizontal little segments, y equals 0, 1, and 2. Now go the other direction, between -1 and 0. I'll pick a number between -1 and 0. So how about -1/2? What's the biggest integer not bigger than -1/2? Well, it has to be -1 because the next integer is 0, and 0 is bigger than -1/2. So that would have to be -1. Kind of fits the pattern too. And these numbers would have to be -2, and so on. Okay, so how do you graph these? Well, let's just do the one I put in the box here first. Between 0 and 1, all those numbers are going to be 0. So that means at 0, close circle because it's equal to. All the numbers in between are going to go to 0. When I get to 1, though, has to be an open circle because it's not equal to there. From 1 to 2, I jump up and everything's going to be 1. So 1, 1, close dot, right? So at 1, it's 1. Everything between 1 and 2 is still going to be 1 until I get to 2. Then it jumps up to 2. And we keep going. It goes infinitely in both directions. The ones we had going the other direction, between -1 and 0, closed dot on the left, open on the right, closed on the left, open on the right, and so on. It's called the step function or the greatest integer. So those steps are representing those horizontal intervals where everything's equal. Good real-life example of that is something like the cost of an item, like the price of a stamp. For a while, it might be 44 cents, and then it jumps up to 47 cents, and then it jumps up to, so these are jumping up to these flat values. It's going to stay that same amount for a while, and then it jumps to a new price. This is definitely an example of a discontinuous graph because it is not connected. Okay, so that's something that you're not familiar with. Let's take you back to something that you might be, an example of a graph that is actually, that you've done before, that really fits into this piecewise sort of idea. So absolute value, I want you to think in your head, what does a graph of an absolute value look like? What shape does it make? And it makes that shape of a V. So if you remember what it looks like, you can go ahead and graph it, but I'm just going to put in some values just to make sure you can see what that picture looks like. Answer to an absolute value, always positive. So do enough points so you can see what that graph would look like. And we'll plot those points so it makes this V shape. Now I'm going to argue that this is actually a piecewise graph. It's a great example of one. And here are the two pieces. So I'm going to label them here. So this first part in quadrant 2, I'm going to label that piece number 1. And then this part, starting here, I'm going to label that piece number 2. So this graph actually is like two lines or line segments coming together at that vertex point at 0, 0. So we could write one of those rules that you saw in that first example of what piecewise graphs look like using function notation. So f of x, this is a function, right? It would pass the vertical line test. It's going to have two lines in its rule. So however many rules you have, use a brace to show that that's a set of rules that are going to be grouped together. So these are all the rules that describe this graph. We're going to see if we can figure out what the equation would be for each part of this picture. So let's look at the blue part. So this one right here. What is the slope of that line? Down 1 over 1, down 1 over 1. So the slope would be -1. Y-intercept is at 0. So in slope-intercept form, that would be -1x. And when are you going to use that? So we say if, now we're going to do the interval of domain. For what x values is that true? Well, it's all of these x values all the way up to 0. So all of the x's that are less than 0. Now, if you want to, we can go ahead and include 0 because it does include that point on the graph as well. So we can put it in this piece of the graph, or you could put it in the second piece. It really doesn't matter. So that's the equation of that part of the graph. Now, normally, if there was no limitation, you could continue in the other direction, and that would be the whole line negative x. But the graph doesn't have any points down there. It bounces back up. So this part of the graph is chopped off. That's how I think of this piecewise part of it. It's only that piece that stops at 0. Okay, let's look at the other piece of the graph, this number 2, the red one. So what would the equation of that ray be? Well, you're going up 1 over 1, up 1 over 1. So the slope is 1. And y-intercept again is 0, so plus 0. If, now where are those x's? Where do they start? Well, the first point on the graph is at 0. And it's all the x's that are bigger than that. So when you look at the domain being split into these two chunks, you have all the x's less than 0 and greater than 0. That's where this graph changes direction, and we have a different rule. Something else is happening. Now again, you could have put the equal to on the red one or the blue one. It doesn't matter. That point at 0, 0 is included, so it needs to be on one of them. So really, absolute value is a piecewise graph. They don't want to write this big rule every time, right? That looks kind of scary, the big f of x. So we use absolute value symbol, but that's what it means. It's a piecewise graph. So as just a quick review of some of the graphing that you did last year for absolute value, let's take a peek. So you're looking at 3 different things that happen to this graph. So let's see if you can figure out what those are. What does the negative sign out front do? So think about that. What does the 3 do? And what does the plus 2 do? And if you know that, you can go ahead and just make a sketch. If you don't, then we can make an XY table. I'm just going to put in 3 values. We know what shape it should be, though. It should be a V, so you have to do enough points to be able to see the V. So if I plug in -1, absolute value of -1 would be 1 times -3 plus 2, looks like we'd be at -1. Plug in 0, that would be 2. Plug in 1. That would be -1. So if I make this graph, let's see if your predictions about what these numbers do are correct. So the 0, 2, that would be up 2. So that's what a plus 2 does. It moves your graph up 2. Points are at -1, -1, and 1, -1. So the V going in this direction. So the negative sign makes it reflect over the x-axis, and the 3 makes it steeper. It's a vertical stretch. So instead of the slope being over 1, down 1, it's over 1, down 3. So you're going 3 instead of 1. So the slope is a little bit steeper. So again, there's 2 pieces to the graph, really, right? If you think of it as piecewise, here's piece number 1, a positive slope line, and then there's piece number 2, a negative slope line. So technically, it is a piecewise function, and this would be one that I would call continuous, right? It's continuous because you don't have to lift your pen or pencil to draw the complete graph. All right, now let's get into the real deal here. We're going to talk about these ones that have different rules for each part of the domain. So let's see if we can kind of walk through that and figure out what these different rules are saying and put them all together and make our entire graph. So what's helpful to me is I like to label these. So 1, 2, 3 here. I have 3 different lines, so there's going to be 3 different rules. I'm going to color code them too to make it a little bit easier. We're going to try to keep track of each of these rules separately and put them all together on the same graph. All right, so rule number 1. I'm going to use y equals for the f of x. That's the same thing as y. So I'm just going to use y because I think that's easier for people to look at. Whatever comes after on this very top line here is going to be the equation that we're going to graph. Anything that comes before the word if. So it's y equals 2 is going to be that equation. So now think about what is y equals 2 graph as? And that's a horizontal line. So normally we'd be drawing a horizontal line across the entire thing at 2. Now don't do that because we're not going to be doing that entire thing. We're going to be chopping it off. So it's not that whole line. We only want to do it for the x's that are less than or equal to 0. So if you think about that picture, less than or equal to 0, that means I'm stopping right here. It's only going to be this part of the line. So I will talk you through how I like to do it. I like to make a little table of values. So some people can look at the big picture like that. You know it's supposed to be horizontal. What I always do is I think about what number they give me. It's a 0. That's where they want the domain interval to stop. So I know I have to put a 0 in there. Whether it's equal to or not, I'm going to put those domain values in that they give me because that's the place where my graph is going to either start or stop. So I know I have to put in 0. And then they want all the x's that are less than 0. So let's put in another number that's less than 0 as well. So how about -1? Just be easy. Now this is horizontal, so you know that your numbers are just going to be 2 for both of them. It's horizontal, can't be anything else. So I know where those lines are going to go now. So where that ray is going to go. At 0, 2, it's going to be a closed circle. How do you know? Right? Equal to. And then at -1, 2, I could keep going. It's going to be this part of that line. So that's piece number 1 in my piecewise graph. It's a horizontal line, but I'm only doing the part that's less than 0. So think of it like you took a scissors and you cut it in half. So we're only using that ray. All right, number 2. Equation number 2, y equals again. Look at what comes after the brace and before the if. I underlined it. So the equation for the second one is y equals x plus 1. And I'm going to make a little table again for this one. For what? Well, it's for all the x's that are in between 0 and 2. So now I know you guys could graph what x plus 1 looks like if you were going to do the whole thing. So think about it in your head right now. If you were going to graph the entire graph of y equals x plus 1, what would your y-intercept be? Well, you put it at 1. Your slope would be 1. So you go up 1 over 1, draw on the whole graph. But what we're saying is, for a piecewise graph, I don't want the whole thing. I don't want that whole line. I just want the one that starts, part of it that starts at 0 and ends at 2, just that little piece. So you have to put in 0. You have to think about 2. I know they're not going to be equal to. Look at the inequality. There's no equal to's there. But that goes right up to 0 and 2, which means you can use open circles to show those locations. So you need to put in the 0 and the 2. So put those into your equation. So 0 plus 1 and 2 plus 1. So I'm going to have the point 0, 1, which is open, and 2, 3, which is open, and that little piece of line in between. Now again, normally, you would draw the entire line. So it would continue up here, it would continue down there. But when we're using this piecewise sort of idea, we don't have the rest of it. Think of like cutting it off, and you're only getting that one teeny tiny little slanted piece of that line. So from 0 up to 2 for x. Okay, part number 3. Your third equation is y equals, look at the bottom line, -2x. For all the x's that are greater than or equal to 2, which means you absolutely for sure should be putting in 2, but then you want something bigger than 2 as well, so I'm going to put in 3. So plug them in. That'd be -4, -6. You're going to have a closed dot at 2 because it's equal to. So I'm going to have a closed dot at 2, -4. And then I'm going to go to 3, -6. So I know I'm going in that direction, and I'll have that ray. So again, instead of continuing back into, quadrant 2 there with that entire line, you're snipping it off, and you're only having that ray down in quadrant 4. Some people, instead of putting in the 3, they'll just do the slope. They'll say, oh, the slope is -2. So that means from this point, go down 2 over 1, and then I have that ray in there as well. So that's a possibility too. So that's my third part. I guess I didn't label this middle one. That's part number 2. Now you don't have to label them on your graph when you do that. If it helps you, it's just kind of a way to keep track of it. So would this be continuous or discontinuous? I have to lift my pen or pencil, so that means this would be a discontinuous graph. All right, so that's a great example of a piecewise graph. All right, so we're going to finish off here. We're going to do a couple more here. I think, just in interest of time, I'm going to skip to the last one, and then if we need more help, we can always come back and do that other one. So let's do this last one. So piece number 1, piece number 2, and piece number 3, just to give you an idea of the different kinds of things that can happen. So piece number 1, y equals, let's see what we've got. In front of the if, -2x plus 8. Okay, I'm going to give you a second, or maybe pause the video. You write the other 2 equations and see if we come up with the same things. So see if you can write the other 2. So go ahead and pause, do that. So second one is y equals 5. And then the third one is y equals absolute value of 3x. So hopefully you can figure out the equation part. All right, now let's figure out the domain part so we can actually see what points we're going to be graphing. So for the first one, make my little xy table here. I want all the x's that are less than or equal to 1. So absolutely have to put in 1 and pick a number less than 1. So I'll just do 0 and plug them in. So go ahead and do that. So plug it in a 1, that'd be 6. Put in a 0, that would be 8. Now at that 1, it's going to be what kind of a dot? Closed, because it's equal to. So 1, 6. And then we have 0, 8. It's going in that direction. And we have that line segment going back. So that's part number 1. So again, it's not the whole line, it's just that piece. Okay, middle one, this is kind of interesting. Y equals 5. That's horizontal. But instead of having the whole horizontal line, they just want a piece of it. And this piece, pretty tiny, what piece do they want? Well, they only want x equals 2. So it has to be 5. So what is that going to look like on your graph if it's just 2, 5? Well, it's just the point, 2, 5. All right, last piece. Absolute value should make a V. Now here's the thing. If you have only a piece of the graph, you may not see the whole V. So don't be alarmed. You may only see one part of a ray or something, or you might see the whole thing. It just depends on what the interval is of the domain they want you to do. So they want you to do all the x's bigger than 2. So I'm going to start at 2, something bigger than 2. How about 3? Plug them in. Open or close, circle at 2. So look at your inequality. It's just greater than, so it has to be open. So 2, 4. And then we have 3, 6. Let's see, 4, 5, 6. So we're going in that direction. And we have that third part. Now, when I look at that part number 3, it's definitely not a whole V. It's just the piece of that end. If I kept going with what the V was supposed to look like, it would come down to 0, and then it would go back up on the other side. I don't have all that, though. Remember, it's a piecewise graph. It's only the part that is 2 and bigger, open circle. So this would be a continuous or discontinuous. Not connected again, so it would be a discontinuous graph. And that's how you graph a piecewise function. So write out each of your equations, and we graph.